just like to welcome the two presenters today, who are going to be talking about, well, it's about the user interface, graphical user interface. But as it turns out, there's a lot that goes into that, and we're going to be talking a bit about human factors and usability engineering today. And the first presenter is James Brennan from Tiller Design, followed by George Borisk from Genesis, and they'll be tag teaming on this presentation. So I'll just get both of you to say hello.
Hello, this is James.
Yeah, hi, this is George.
And so we'll start with James. And just before we get into the slides, James, you were telling me that your passion and interest in this initially came from B-52 bombers.
Actually, the B-17, which was a program at the end of World War II. Yeah, as I mentioned to you, Tim, you were joking with me about the number of slides I've put together, but I actually had a whole section on the B-17 and the development of that. That was really where human factors and usability engineering was born, because the Air Force couldn't work out towards the end of the Second World War. They had more than 500 crashes in the last year of the war of B-17s inexplicably diving out of the air and crashing. So with 500 crashes and up to 10 people on those planes, there was an enormous loss of life. And at that stage, they characterized those crashes as pilot error, because they assumed that because pilots were being turned out in droves, you know, as ramping up for the war effort, that it's probably conceivable that they weren't as well trained as they should have been. But they actually took the step of putting that problem in the hands of clinical psychologists. There were two very famous guys, Paul Fitz and Alphonse Chapanis. Now, Chapanis is a very interesting guy because he was really the guy that actually started to understand that humans interacting with devices, that the paradigm was wrong. That instead of creating complex machinery and expecting humans to interact with it and adjust, that perhaps the problem should be framed in a different way, which is, how do we get those intelligent, smart machines to actually take into account human frailties, cognitive abilities, and you know, experience? And that clear insight was the thing that actually drove the development of human factors as a discipline. And Chapanis actually went on.
Frailties.
Yeah.
So those frailties are what we call human factors. Yeah.
Yeah. And it's a fascinating area of study, and I'd welcome a chance to have a chat with you in more detail about it at some point. But you know, and again, these disciplines and concerns became very much interwoven with the way both aeronautical design and also automotive design. You know, there were things that he created which were pattern shaping, which is the subtle differences that we have in the controls of devices so that we can intuitively understand what they do. So after he'd done his work and they made the modifications, they didn't have a single crash after that. Just absolutely amazing. I find it incredibly interesting field. Now, the medical device industry has been a little lax in terms of adopting some of this, but it's now become an absolutely critical part of device development to try and minimize harm and risk of the things that we all get involved in designing.
My sense is that in the past, the medical devices have really come from a, you know, paradigm of you know, starting with the pharmaceuticals, which is, you know, is there something about this device that might kill the, you know, the patient, you know, in terms of the drugs, or, you know, electrocuting them, or whatever it is that the device is doing, radiation therapy, you know, maybe frying them. But with the advent of software, and particularly recently, you know, the concept of software as a medical device, the whole user interface has really become the subject of a lot more focus in recent years, hasn't it?
Yes, it has. Yeah, and you mentioned, you know, there's a corollary. There's a similar problem with the administration of drugs. in doing my research for this talk, I came across a situation in Sydney only a few years ago where there was a death which was caused by someone grabbing the wrong vial of material, which looked almost identical to the one sitting next to it, but of course they had completely different clinical outcomes. And that vial was injected into the person and they died. And it would have taken a very disciplined, trained eye to actually tell the difference. And when you've got someone operating under extreme duress and in a noisy, crowded environment, which medical environments often are, it's not surprising. The only surprise is really that we don't have more of these problems.
Well, let's crack. You do have a lot of slides, so let's crack into it.
Yeah, I'm in the position of having to do the 2-minute waltz in 1:40, I think, but I'll do the best I can. I mean, I'll try and get through them as quickly as possible. So this segues very nicely into what we've just been talking about, that human factors and usability engineering are now a critical part of medical device development. By the way, I won't try and talk to all of these points. The slide deck will be available to anyone who wants it afterwards. So medical areas, it's a significant problem. There's the research that I've done, there's two figures that are given, usually 100,000 or 250,000 deaths per annum in the US healthcare system. Now, if either number is remotely close to being true, then that's a serious problem. And again, what I was talking about with Chapanis's work, we're now talking about these as design issues regarding the user interface rather than an error caused by the system. There's now a more disciplined regulatory imperative in terms of undertaking this work. Both the FDA and also the IEC have binding standards. The FDA it's got a number of recommendation papers, they've been formulating that for the last couple of decades. But it's absolutely a necessity now and mandatory that these standards and guidances are included in risk management as we develop medical devices. So those human factors and usability engineering sit alongside all of the risk management processes that we undertake in medical device development. There's also a number of related standards which point towards things like the use of graphical symbols, the enhancement of the controls, software user interfaces, workstations, mobile displays. All of those are codified, and it's an extensive list of standards that you've got to be aware of as you design these. There's just a picture of some of the icon development that the FDA, they're not very keen on anyone going off the reservation. These things are codified, and they want them used in a systematic way. Now, of course, as we talk a little bit further, this has to be relevant to the people using the device. So the cohort of users is critical in terms of whether they understand it, whether they're used to these standards, and so on. So it's always the bottom line is always to create these interfaces that the people using them understand and can interact positively with.
James, can I just ask on those, if you wanted to create your own, were you saying there that you have to use those ones that the FDA decided, or?
No, you don't technically have to use them, but you have to have an incredibly good reason for diverging from common standards. They're very keen. The FDA is very keen on standardized approach to this stuff. Of course, there are things there there are icons. For instance, we're doing a development at the moment, which is going to be used in developing countries in Vietnam. Now, there are up to 14 different languages there, so we're developing an icon set that people can use and understand without the problem of trying to do the graphic identification of different languages. So it's not a hard and fast rule that you can't develop your own icons, but you've got to have a good reason. So some of these outcomes can be catastrophic. And I just use this as a single point of why it's important that we do this. So there was a recorded case in 2000 where a 19-year-old mother who had a routine cesarean was accidentally the infusion pump that was being used on her was accidentally misprogrammed by the nurse. And she had inadvertently set the pump's concentration setting lower than the concentration of the narcotic that was being loaded into the pump. So for every ml of narcotic solution that the pump delivered, the patient was actually receiving an amount of drug that was several-fold greater. Now, you can only imagine the human damage that that did to the various people that were involved. And it's all because of lack of clarity and the design of the user interface not being done properly. So usability engineering is closely associated with risk analysis. As we talked about at the beginning, it's becoming an extremely important part of the development of medical devices. So in our normal risk analysis, we're used to analysing all sorts of hazards, the physical, mechanical, thermal, electrical, chemical, radiation, and biological. Now these hazards are generally associated with instances of the device failing. But medical device hazards associated with user interactions should also be included and are now extremely important. So this is a flow chart which is closely aligned to ISO 14971. So we're following the, in all of the work that we do, it's a creation of, it's a very similar thing. So we're identifying the hazards, we're establishing the level of that risk. We try and understand what the likelihood of that risk happening is to develop a risk profile for that particular hazard. Then we try and define how we mitigate that risk and then test and report. And of course, through the normative testing process, we then may have to rinse and repeat and come back, and that may be a loop until we end up at something that is working, that is have a low level of risk and a high user understanding. So what are the effects and cause of user-related failures? Basically, we're trying to make sure that the user interface design doesn't cause the user to fail to adequately understand or perceive what's going on with the device. Some user-related hazards are more serious than others, and that, of course, depends on the severity and the potential harm to the user. There are three main factors which contribute to the success of a user interface. So that's the design of the interface itself, which we'll get onto in a little bit, where we're going to be talking more about graphical user interface. But I want to draw the larger picture that the user interface is not simply the graphical user interface, it's also a whole range of other things. We've got to consider the cognitive and physical abilities of the user cohort. So exactly age, status, sex, gender, what their previous experience is, how they relate to technology, and etc. And also what the environment of use is. So user interface is a very broad term, and it can mean a lot of, there are a lot of components that can actually, that are part of a user interface. So the ergonomics, which is the way that human beings interact with a device, could be the size and shape of, shape and weight of a handheld device, what auditory signals, buzzers, alarms, tactile feedback, haptic, it could be a mechanical detent, what visual feedback we give the user, which is maybe LEDs.
So,
yep.
James, what's a detent?
So a detent would be a mechanical click.
Detent?
Mechanical click. So like a spring-loaded ball bearing on a knob. So you can actually, a lot of these analog, you know, when we test this with users, a lot of old-fashioned analog things actually work better, because you can actually operate a knob with a detent and a click while you got your eyes on something more important. So it's always a combination of things working together. We're not actually designing usually a device which has just got a graphical user interface. There can be quite often a combination of things which the user has to operate. So you've got to harmonize all of that and get it all working properly. So point 5 is what we're going to be talking about, which is the graphical user interface, or GUI. It's usually a symbol icon-based architecture that guides the user through a series of steps. They're usually trying to find out something or enter some information or get some feedback. Controls which house the GUI might include keyboards. You might be using a mouse or a stylus or a touch screen. And of course, we've got the burgeoning new field of augmented reality and virtual reality. We're talking now about gestural, eye gaze, and voice commands as well. So that is going to open up a whole new range of complexity that we'll have to deal with.
Yeah, just while you're on that, I'll just share an example of that, which Genesis is doing, which is it's a virtual reality rehabilitation system for people who've had a brain stroke and they've lost the use of their hand, the coordination, just things like picking up a cup or a toothbrush, and in the wiring is all still there. There's nothing physically broken. It's just that the neural pathways are not there. So you need to regenerate the neural pathways. And apparently, if you simulate the environment and you have a tactile feedback in the arm, then you can accelerate the regeneration of the neural pathways. So that's just an example of a virtual reality system. And that company is Neuroimmersive, which is one of the Cicada spin-outs. So
yeah,
it's certainly on our radar quite a lot now.
Yeah, and again, I guess the overwhelming point is that these new technologies, we've got to work out a way as designers and engineers to actually enhance the human experience and actually make everything better.
Yeah. And there's no standards on that yet.
No, and I mean, someone said to me the other day, a lot of this is common sense, and yes, it is common sense, but you've got to do the work. You've got to immerse yourself in the problem. You've got to turn up and watch and observe and actually target your response to the people that are going to be using this. So user interface can also have other things, things like counterbalanced arms and things. You've got to understand how it's got to be a Goldilocks solution in the sense that those counterbalance arms have to operate as you would humanly expect them to do, and they can't frustrate you by being too slow or not being accurate in terms of the way you wheel a screen or another device. Again, it's a matter of getting everything just right, or as close as you can. Hardware interfaces, so we've talked about that. You're quite often operating with a graphical user screen, but also there can be buttons, knobs, dials, switches, and that sequence, it's like a ballet. You've got to get all of those things harmonized to make them work properly. And it can even include things like packaging and instructions. So how does the person using the device, how do they understand how to use it? Is it something that is reflected in their experience, or can they heuristically understand the way a device works and work their way through it, so that their interaction may not start perfectly, but they gradually get in the rhythm of the device and understand how it works. The second is the cognitive abilities and physical abilities of the users. So the intended users of the device should be able to make use of it without, should be able to use it without making use errors that could compromise the medical care or patient or user safety. The ability of the user to operate the user interface depends on his or her personal characteristics. Things like physical size, strength, and stamina, their education level, their physical dexterity, flexibility, and coordination. Again, with fine motor controls, with analog devices, with knobs and things, it's tremendously important. Sensory abilities like vision, hearing, and tactile sensitivity. Cognitive abilities, including memory. Can they track through a series, a process of a sequence of events? And there are specific devices that are designed for specific medical conditions, so it's got to be considered. So things like vision impairment with cataracts or retinopathy or macular degeneration or color blindness. each of those different conditions will provoke a different response in terms of what the GUI is all about. Literacy and language skills. So I talked a little bit, I mentioned before that we're doing a user interface for a developing country in Vietnam, which has got 14 different languages. We've got to be careful that those icons that we develop mean something to all those different groups. The mental and emotional health of the person. This is a little bit strange, but often people interacting with a medical device feel terrible that they actually not resent, but they feel a burden that which it's reinforcing their disability, their infirmity. So there are things that, you know, I was involved with a project a while ago where it was a device that people carried portably, which actually was attached to the ascending aorta of your heart. It was an intrusive device. We had to very carefully consider what it was going to be like for the person out in the community and create sounds that reassured them that the device was still on, but didn't reinforce and make them feel worse that they were gravely ill. The knowledge and experience of this or similar devices. So again, that's a cultural understanding. You've got to be very careful not to change the way things should operate. So don't have things turning counterclockwise where existing other devices turn clockwise, for instance, as a simple example. The ability to learn and adapt. And the following point, the willingness and motivation is incredibly important. You've got to have someone who really wants to interact with the device. If they are approaching it negatively, it can throw everything off the rails.
I presume, James, trying to make something fun is probably an important factor there.
Well, yeah, as designers, we talk about, you know, very strange concepts like, is the interaction joyful? And you can look to the consumer world and see the success that Apple's had by simplification and elegance in their design. And it's actually a factor with medical devices. I touch on this point a bit later, that the standards actually even refer to that we're all in this business because we want to create devices that make people's lives better, but we're also doing it for a commercial imperative. And the elegance, the sophistication that you can bring to this, you know, basically, you know, simple is very hard to do, but it's also commercially very powerful. That if people enjoy interacting with the device and it reflects the way they, you know, again, not to intimidate, not to confuse, not to make them feel that they're not getting a grasp of things.
If you just go back to that previous, back to the previous slide, there's one other question. It's obviously, this seems to be very much predicated on a patient, you know, somebody who is, you know, incapacitated in some way, and taking that into account. But if you've got a device that's being used by a therapist, you know, a doctor or a nurse or, you know, physiotherapist or some other professional, is there a certain level of competence that you can just assume? And I had this very interesting discussion the other day on a particular project. We were talking about, you know, having a mobile app, and I was arguing that the main reason I wanted a mobile app involved is so I could use a keyboard, because I'm actually was a journalist in my past life and can touch type at 200 words a minute. But the people I was talking to were saying, well, no, actually, I'm used to texting, and I'm very happy with using a touchscreen interface. And something which is more like a mobile phone touchscreen, which I absolutely hate.
Yep.
So it was just really, it was just sort of interesting, those different comparisons, and just what level of assumptions can you make about the user?
Well, you can make lots of assumptions.
You know, therapist.
Well, again, it's never a single audience. There's always a range of audience of people that have to interact with the device. They could be even maintenance staff. It could be the IT staff, which give you various different levels that you move through with the graphical user interface. But you can make as many assumptions as you like. But the whole point of doing this work is to go and observe and actually test. And if it fails, come back, set some new parameters and test again until you find something that is driving towards what you're after, which is reducing risk, increasing clarity, making it easier to use.
Thank you.
Yeah. So I've just been holding on this slide for a little bit because I want to illustrate the point. The next discussion is about the environment of use. So graphical user interfaces often are positioned. This is not atypical of what you will find in operating theatres and medical devices. Even devices that are used in patients' home are quite often not optimally set up. There's always competing screens, there's always competing noises, auditory signals, lights flashing, and again, it's a case of testing until you find something which is aligned with what the requirements are in terms of creating a device that's really useful and safe. So there are some things which, you know, we've talked about. These environments are often cluttered, stressful, and noisy. You've got to find a way of making the device that you're designing fit into that environment and be useful. There can be some counterintuitive things, like the lighting level might be too low or too high. If it's too high, you quite often have problems with reflections on displays and things, and the glare on the screen. The noise level might be high, making it hard to hear device feedback signals. Now, there's also a noted syndrome with clinical staff in that they get like a car alarm sensitivity, where things go off and there's a ping fatigue amongst clinical staff. So there might be subtle changes in the way that the auditory signal is conveyed that makes attention and also distinctively identifies that device. There might be multiple models of the same device within, such as there's quite often a stack of infusion pumps, for instance, and you've got to make sure that yours is the one that gets noticed. The room is often full of clutter, but it's also often filled with other people and activities happening on. So you've got to make sure that lines of sight, that the device is positioned correctly. This device could be in a moving vehicle like an ambulance, so you have to deal with vibration, and then you find that you've got difficult to perform fine motor movements as part of that environment. So now I just wanted to jump to try and highlight some of the key factors in the design process. And this is, Tim, this actually just draws on the thing that we've just been discussing, that even within the standards and the collateral recommendations, the guidances, they actually highlight this point that human factors, it's not only about making it safe and effective, but it's the elegance and beauty of the interface is what appeals to us emotionally. That's something we live every day as designers and engineers, but it's worth reinforcing here that what we're doing is enhancing the commercial viability of the project we're working on.
Yeah, and actually one of the things that part of the reason I'm in this role is that I am an engineer, but I've also been a journalist most of my life and in marketing. So I sort of straddle the fence between the, coming from an engineering perspective, just make it do what it needs to do, versus, hey, it's got to be sexy as well. And I do know that particularly when you've got a market that has incumbents in place, and if they're a bit clunky and they don't look so great, then often that brand appeal of the new device disrupting that, the brand is a very important part of the market disruption process, which is a key part of medical device development. It's not all about the technical side of things. So yep. I really appreciate what you're saying here.
Yeah. Styling per se gets a bad rap, but it's really important because we respond to things emotionally first before our logical side of our brain kicks in. And I've seen it so many times, even with quite sophisticated people that are very detailed researchers and things. They'll pick something that they'll be attracted to something because of its look and its form. And we cognitively give those things that look like they've been more highly resolved, we give them more points intellectually that they are in fact more highly resolved, where sometimes it couldn't be further from the case. So the process that we follow, it's very similar, and it would be very easily understood by a lot of us who work in hardware device development. It's a very similar process. We're driving user requirements, which the user needs. We develop designs, build prototypes, conduct formative tests, and conduct validation tests. Now, in human factors, formative test has a quite specific meaning, which is interacting with users. It's a process which allows interaction, questioning, observation in the early stages, and as you move along this line, the prototypes and things are getting more sophisticated. These days, in the following slides, I'll just show you some of the process, but you end up usually with clickable prototypes on a device that can be put with actual users in the environment to actually do some of this these testing to actually try and refine it. These are some of the things that the way that we work through. So these are rough prototypes and sketches trying to work out the hierarchy and interaction of all the various elements and buttons. In the old days, we used to do this literally with it was called paper prototyping, and you'd actually have lots of toilet rolls or rolls of paper, which you'd post-it notes, which you'd try and map all of this out. These days it's more sophisticated, so there can be more sophisticated hand sketching. There's a lot of software that allows you to map all of these interactions. And it's always the user experience flowchart. You've always got to make sure that you understand the type of user, the hierarchy of information you're trying to display, things like color. Tim, you touched a minute ago on brand identity and marketing. Quite often we're presented with a style template, which is the organizational style manual for everything that they do, all their marketing material. And you've got to be very careful sometimes in translating that to graphical user interfaces, because, for instance, the branding colors might be red, black, and gold, which have got, red is used very differently in a graphical user interface. So you have to be careful about how you apply those style manual guidelines to what you're doing with these.
And I imagine also red is a certain meaning in medical devices quite often.
Yeah, it means danger or error or an alert, and sometimes you've got to tiptoe around that to find the right balance. So this is another example of a commercial. This is Adobe XD, which is another way of putting things on devices. And again, all those all the little interactive things here are trying to work out what if. You've always got to give people a way of navigating easily, so that then, again, you confuse them and you've failed. There's always got to be some way of coming back to where you came from, and so on. So this continual refinement and testing, and also consideration of standards. The one on the left, not necessarily bad, but the one on the right is a more enhanced device, which is, again, dealing with the critical information and presenting that more graphically in a better format, more easily understood. Similarly, on this is a hemodialysis machine, this is the evolution from a completely numerical to a more graphic. It's got limits so that you can understand that the machine is operating correctly. So again, following that process, it's very similar to risk analysis that we would do with a hardware device. This is basically the capturing of user needs at the start of a project. So there are various things there that should be given more importance, and that feeds into design inputs and requirements, which is just exactly like our risk management documentation that we generate. And that leads to, again, prototyping and testing with users with various layouts and configurations and orientations of information on a screen. And it's always a case, formative testing, put it in front of users, put it in the right environment, and observe the results. There's a number of collateral standards which help here. So HE75 is it's a collateral standard which actually points to software user interfaces, hand tools, visual displays. So it actually gives you quite a detailed checklist in terms of how to enhance. So how to enhance graphical displays. So you see the one on the left, which is the one before these standards are applied, and then you see a new device which has got a different screen, and again the important information displayed more clearly. Similarly, this is another. It's a large volume infusion pump. This is the before and the after when they were considering how to create user alerts and things. Now, finalizing the design, you've got to make any changes based on formative usability tests. You develop the final screens and actual software in partnership with the software developers. So George will be picking up on that, I'm sure, in the next part of the talk. Hardware, software, and support materials, including instructions for use, are completed, conducting several more normative usability studies to validate the risk. And then there's always a final summative usability test to validate the design for formal validation. So by the time you get to the summative test, there should be very little change. It should be a highly resolved design that is basically passing that last hurdle before it goes into production. And I was just being a bit mischievous there, Tim. I put that picture in because I knew you'd ask me about it. You there, Tim?
Sorry, I had myself muted. Yeah, and it does look very interesting. And we actually had a case study on a device that measured brainwaves just recently. If you go back and have a look at our webinar recordings. But and just for those, the summative, we talked about formative earlier. Just to clarify for people, the formative is usually just a small number of, maybe 10, 20 users where you're just gathering information, and then the summative or the validating tests is where you have, maybe several hundred users.
That's right, and it's usually, yeah, I mean, you don't get to a summative test without, it's the final design essentially, so minor tweaks are allowed. Whereas the normative or summative tests, as they're called, allow a degree of interaction from the researchers. So you're allowed to prompt respondents to try and understand what their mental state is, if they're getting confused, if they're needing more information. So it's really a collaborative endeavor, and that all funnels up to a single, final design, which is the summative test. Okay. So I'm just conscious of time, so I better get the skids on. You've got to, so a useful thing is to, devices come in a wide range of sizes and shapes. So it's possible, if possible, you try and test how the design adapts to various, both the largest and the smallest displays in terms of scalability and legibility. There's various different types of configurations and systems. So UI designers call them responsive, adaptive, and embedded. Responsive and adaptive are essentially web-based. Responsive can operate across several different devices. Adaptive is a bit more of a constrained, you've only got a few layouts that are interacting with the device. And embedded is, as it implies, that it's a specific bespoke device that fits to a piece of hardware. Counterintuitively, the point is that consumer rules don't apply in terms of graphical user interface. So Tim, you and I a few weeks ago were talking about skeuomorphic design and what that means. It actually usually comes out on top in terms of the user testing when you do it in a medical environment, because skeuomorphic design actually adds more context, a richness that is not available with flat design, which is the current state of play with things like the Apple operating system and Android systems. So in this environment, it can actually work better. Similarly with icon development, the icon on its own with no color usually is not as successful. When you add borders, shape, contour to a button, as well as legible legible text, they're often more successful and they test much better. You've got to make the information that the respondents are trying to read, make it legible. And again, these standards are quantified in HE 75. So it defines the viewing distance, the angle of view, the size of the type that you're reading, and so on. Make sure that it's in a how quickly the text needs to be read, the figure to ground contrast ratio. So not everything needs to be high contrast. It's only, again, it comes back to this hierarchy of information. The most important things are in high contrast. Consider the lighting conditions. Font style is important because there are many fonts that render more accurately on a pixel environment than others. So that's a whole art in itself, picking the right font, the right size, and so on. Counterintuitively, sometimes displaying critical information is important. A lot of nurses and things like to have a constant reminder of the patient name and identification, and this consistently tests better than something which is less rich. And again, that's going against what would happen in a consumer environment where they're trying to distill it to the simplest possible form.
Good. And actually, can I just, there was a question from the audience, which I think you've kind of answered with that. The question was from D. Hood. We spoke about UI design concepts being referred to as common sense. What are some standout examples of that not being the case, e.g. counterintuitive learnings from user testing? So this would be a really good example of that, I imagine.
Absolutely, yeah. And again, your point earlier about the assumptions that you make, you can certainly make assumptions at the beginning of a project, but you test and test and test till you're blue in the face, until you're absolutely sure that you've got a hardened system that is elegant and does what you want it to do, which is reduce the risk. And sometimes you get counterintuitive results. I mean, the previous slide about the Skuomorphic design, most consumer people making user interfaces would not. It's been largely discredited because, quite frankly, it was seen by many people as being ridiculous that you were representing things on a screen that really had a resonance with something that shouldn't be there, as is the name Skuomorphic. But in fact, when you use it in a medical environment, they actually perform better and they're clearer and people understand them. So give people the chance to make unsafe changes. So make sure that they always know where they are in the process and that it's clear what has been saved and what hasn't been saved. It seems obvious, but again, you've got to deal with a human being who might be unsure, who might be operating at the end of an 8-hour shift. You've got to make sure that you give them the options that they clearly understand where they are in the process. Incorporate automatic checks. So this is one of the, we talked the terrible outcome earlier. It's getting much better, but we have things like the 10 times error, which is, again, it came out of the aeronautical industry where pilots were crashing into the sides of mountains because they'd misread their altimeter, thinking they were at 50,000 feet when actually they were at 500 feet. With particular fonts, the letter 7 can be misread as a 1 with terrible results. There can be physical masking by the edge of the display. You've got to make sure that there's enough border between the physical hardware, the plastic enclosure, and where the display is mounted so that it's not throwing a shadow that can actually obscure some critical information. So all of those things need to be checked, and you can also have software limit values that actually highlight that there's an error. So 1000 BPM is clearly an error, and an intelligent machine can help pick that up and then feed that information back to the user. Support critical decisions and interactions. So again, it's that this also has a reflection in consumer devices, some of this stuff drives us nuts, where we're asked to constantly confirm about what the actions that we're taking. But it can be absolutely critical in a medical device sense that you actually control that. This is an extension of that, where you're letting the user know where they are in that process, that sequence of events that's going to be critical.
I don't want to distract too much from your good pace that you're going. I just wanted to sort of reiterate that point that you made about software doing parameter checking on displayed parameters. That's a real key design element to defensive software programming, so that you ensure that any parameter that is used, regardless of whether it's displayed or whether it's being used for some kind of additional actions, is actually range checked and has an acceptable range before it actually gets used. So that's a real good sort of point to make there.
Yeah, it's an important. Sorry.
So for those of you who joined late, that was George Borisk from Genesis. He'll be taking over from James's presentation, dual tagging in very shortly.
Okay, yeah, it will be shortly. I'm galloping ahead. So things like making the decimal values distinct. Again, this is the transmission of information, making it clear. So actually go in there and actually increase the pixel count on a decimal point. Provide robust help solutions. So we quite often, when we're designing mechanical devices, if we're gathering people who we want to interview about the device, you don't take the people that actually hum along quite happily and use the device the way. You quite often learn more from people who are the ones who break things. So we get them in and we try and understand what is driving them about the way they interact with the device. And the support situation is very similar in that some people will want more, some people will want less. So you've got to find the balance between all of that.
This is a good segue to another question, James, from D. Hood, who said, what are the most challenging aspects of user testing, perhaps e.g. getting trustworthy feedback and not accidentally biasing the responses?
Yes, that's true, but you need, the biggest problem with getting that feedback is coming to the table with too many assumptions yourself. The worst designers that we have are the ones who presume to know what the solution is before we start. So you've got to, it's a special nuanced skill where it's observational research, and you're actually making sure that you get the right information to act on, and that you're prioritizing it properly as well. This slide picks up a little bit on what you were talking about initially, Tim, which is there's going to be a number of different people that interact with the user interface and who have different requirements. But there's levels of hierarchy and detail that you have to build into the design, but also make sure that it is relevant and similar to all of those people, but they all have a slightly different nuanced experience with it. Touch target size basically is make things if there's a critical button there, make sure it's as big as it can be within limits. Gestural interaction. So there's a lot of work being done, particularly in the disability area, with the controls that operate wheelchairs and things, which are gestural movements. Again, you've got to approach this with a bit of apprehension in terms of medical device design. And the thing that wins is the one that works. There's no doubt that this will become more important, but we've got to find a way of engineering it to work properly. And this is my last slide. I think I did pretty well, Tim. I'm at 50 minutes. This is a bit of a pet hate of mine, a pet peeve, how we fail as designers. So this is a picture of something we're all familiar with, a remote control. It's actually the crystallization of things that annoy me in terms of this is a system architecture which designers and engineers get frustrated with other people because they can't operate it at the same level that they can. And they say, why? Why can't you do that? The point is that this is what the market wants, and this is how we help them navigate the world. So that's the end of the presentation. Thank you.
Thank you, James. And I can't resist sharing my new Samsung TV purchase, which did actually do a much better job with the remote control and reduced it down to just 4 or 5 sort of buttons. But then they added a whole lot of buttons for Netflix and Disney and all these other deals they've done with these channels, just to clutter it up again.
Yeah.
Anyway,
well, to me, that's an absolute failure in design, and we shouldn't be putting things in the world that annoy people.
I got to admit, I love the Netflix button.
Yeah. Anyway, look. Thank you very much. And look, there are a couple of questions, but I'm going to, just in the interest of time, I'm going to get George to take over now. So for those of you who missed out at the start of the presentation, we've just been hearing from James Brennan from Tiller Design, which is more on the, I guess, the industrial design perspective. And now we're going to hear the engineering, the software engineering perspective. So George Risk is the head of software engineering at Genesis Electronics Design, and he's going to take us through what happens when you've done all that beautiful design, industrial design. What happens next, George?
Thanks. Can you guys see my slides? Okay. Yep. Okay. Thank you.
Yes, but I'm sorry. I'm only seeing. It's not full screen. It's the. I'm seeing the
reader view.
Oh, sorry, you're seeing the wrong one. Let me stop that share.
You need to change.
Share the correct one. That would be that one. Is that better?
Yep.
Perfect.
All right. Thank you. Sorry about that. That was fantastic, James. It's a pretty hard act to follow, to be honest, but it's fitting that the industrial design experts have nicer and prettier slides than the engineers. So I think it's kind of thematic there. So look, there is a lot of points. I know this is focused on the graphical user interface design for medical devices. There are a lot of points that I'll be discussing today, which are actually fairly generic to software development that goes on a medical device and applies to other user interface aspects that James mentioned in his slides, buttons and whatnot. But I will be focusing on the graphical user interface side of things. And I will note that I'll try to keep this relatively slim and try to go through it quickly. My slides are not, I don't have as many slides as James does, but try to go through quickly. So, okay. So just an example of some different types of graphical user interfaces. So these are not all different types of them, but they're the sort of main key ones. So smartphone displays, dot matrix displays, microcontroller interfaced LCDs. That would include things like touchscreens, by the way. So touchscreen LCD displays and embedded OS interfaced LCDs. So look, there are many different reasons to go down a certain design choice of why you would choose a certain display type. There are things like viewing angles and brightness and the amount of information that you have to display. When you can limit the amount of information, if you have, for example, you're in a theater and you have a fairly low lit area or high brightness light shining on top of your device, there might be something driving you towards maybe using really high brightness LEDs so you can still see the displays. So there's things like that in play.
And George, I know that dot matrix display was actually chosen specifically for a high light level surgical environment.
Correct. Yeah, so that's exactly right. It's a situation where if you had an LCD, the surgeon might actually struggle to see the information that they really need to see. And
so it looks fairly rudimentary, but in fact it's only being released onto the market now and was specifically chosen for those reasons. So I think the thing that really strikes me there is that you don't necessarily go for the great graphic display just because it looks sexy. You do have to go for the most functionally practical choice.
That's right. There's several reasons, and usually you have to drive down. I will point out some other additional reasons in some further slides of what might drive you down a certain choice. So moving on to the next. Okay, so just want to, before I go into the specifics of LCD displays, just a generic discussion on software of IEC 62304. So IEC 62304 is called up by IEC 60601-1. So the it's called up by that headline standard, and effectively it goes through software lifecycle, software class and hazards, so identifying a class. So class A, software can't contribute to hazards; class B, risk of non-serious injury; class C, risk of death or serious injury. Now, your class selection will, in a lot of cases, drive you down your choice of what display you're going to use. Pretty much, if you're a class B or class C, it may limit you quite a bit. Although there are some reasons to continue to use certain displays, regardless of that, but there is additional risks and things that have to be considered, which I'll go over in some further slides. So the items addressed in 62304, software requirements, architecture, coding standards and reviews, software integration, software verification, change control, software maintenance, risk management. So in determining software class, the probability of occurrence of any possible software fault is set to 100%, saying that basically if it can happen, it will happen. So on that basis, that really drives your decision of what class you have to choose. So any risk of non-serious injury is deemed to have 100% chance of occurring. So that you can't say, oh, it's a very rare chance that this will happen, so I'm still gonna be a class A device. So that brings to the next item that gets brought up by 62304, which is SOUP, or software of unknown provenance. So SOUP it's basically software that's not developed under 62304 principles, open source software, operating systems, Windows, Linux, RTOS with the exception of Safe RTOS and some other pre-certified RTOS. And then there's also platforms with the integral software like Arduino, Raspberry Pis, etc. So there are multiple clauses in 62304 that actually impose these obligations for addressing SOUP: specification, verification, risk management, maintenance. And it's effectively dangerous territory. And this says best avoided where possible, because if you avoid the SOUP, you don't have to worry about the implications that the SOUP raises, which is really the added risk, that comes to play. So I'll skip along there. So GUI designs without SOUP. So specifically in this case, just mentioning the dot matrix displays and LCD screens. So specifically microcontroller interfaced LCD screens. So it's not when we say LCD screens, it's quite broad. A smartphone has an LCD screen, of course. That's being very specific to an embedded microcontroller control interface into that LCD screen. So
what you're basically saying is that there's nothing between the microcontroller and the LCD screen. Like in a mobile phone, you've got all the proprietary companies, Samsung's or Apple's, software in between you and the screen that you have to deal with and get through. Whereas that is just a straight path to the screen, so there's no SOUP.
Well, yeah, specifically speaking, all the software that is developed on that microcontroller was developed under the 62304 process and principles. So there is, by definition, there is no use of SOUP, and no use of SOUP just means you can progress through the design and get it certified with a lot more ease and less risk of issues that arise from unknown software in your design. So displaying GUI on screens connected to microcontrollers. This is really just a really brief, quick rundown of roughly how you turn the really pretty displays and images or whatever it is that you want to display on your screens into actual, to make them actually move on to the actual screen. So to display UI elements on the screen connected to a microcontroller, the hardware needs to be designed with this in mind, of course. So either a parallel bus for LCD screens or flexible memory control with external SRAM. Now, all these images and pictures and text all that has to actually be converted into bitmaps. So these bitmaps, so we might get a font file from an industrial designer or a image, and then as a part of the process, we have to convert those images into bitmaps and load those bitmaps onto our software so we can actually display them. So, you know, if your microcontroller supports FSMC, which is the flexible memory control, it's a lot more ideal, as it really reduces clock cycle burden and can simplify the design. So transitioning between screens, now this is quite important. Now, you saw in James's slides that he showed the wireframes or flow charts of how different screens connect together. When a certain button is pressed, what's the next screen that appears? Now, all that design gets fed in, of course, to the firmware, where the firmware engineer will make the decisions based on certain user input. What is the next screen to display? And that's just basically loading on the next image, or so you can do that by, say, for example, if it's just temperature and the temperature is updating over, you know, once a second, whatever it may be. If it's just a certain segment of the display, of course, you can do updates to that certain segment, or you can actually update the whole screen. So from transitioning to a whole new screen, or then you just go and update, you remap the whole bit field of the LED made display. And it allows for things like multilingual support, of course, so like character sets and fonts, and flexible language configuration of screens. So if you have a LCD display and you have a medical device that is being, you know, launched all over the world, the ability to be able to transition between different languages is a key element of that. So moving on. So GUI designs that do require SOUP. So we're talking smartphones, embedded OS interface displays, and PCs/web interfaces. Now, what I'm showing here, so I've got a you know, screenshot of a smartphone app, and I've got over here an embedded Linux display. So an LCD display that is running on an embedded Linux machine. Now, displaying GUI on smartphones and embedded OS processors. So for smartphones, it was as James showed you with those flow charts that he had. Of course, you have to then take those flow charts and then and either, you know, Android Studio or Xcode for Apple devices, you have to then, of course, go and develop those different screens and deploy the app. For embedded OS interface displays, so that's anything on either embedded Linux or embedded Windows, you have to, of course, have the hardware to support that. So things like an IMX8 on the hardware or an STM32MP1, these are embedded Linux devices that you processors that you can put onto an embedded device and host these embedded OSs. And you can, of course, connect displays by the usual means of HDMI, LVDS, DSI, whatever it may be. And then there's things like Qt Design Studio for designing custom displays. That's one particular studio where, in some cases, industrial designers and software engineers can actually collaborate on that tool, where the designers can make the design, and then the engineer can then work with them to actually turn that into actual displays that go on the screen. Right, so the issues with smartphones and embedded OSs. So this is, I mean, bringing us out to my final slide here. We're effectively talking about, well, what is the reason that you would try to avoid using, or why you wouldn't have to avoid, or not have to, but may avoid using these smartphones or embedded OSs. Now, there are obviously certain circumstances where they can't be avoided, and there are many deployed medical devices that have them. But there are certain things to consider when having them in your design. So there are multiple clauses of ISC 62304 which impose obligations for addressing SOUP, specification, verification, risk management, and maintenance. So how do you verify or validate an operating system? Well, the answer is not easily. There are some technical reports which guide developers on how to deal with SOUP. So there are things like using wrappers so that you can actually limit the functionality of what's displayed of what's being used by that OS. So you only have access to those wrappers and you don't have access to all the other functions, as well as the wrappers can be used to do some additional checks like range checking and whatnot. So there are things you can do to try and reduce the risks there. There's some addition. Of course, there is some additional verification. It's driven basically by the hazards analysis and risk management process. And that's the fundamental process you have to undertake if you want to take on these higher level displays. It's really driven strongly by that hazard analysis and risk management process. There's nothing in 62304 that specifically states what extra steps you have to do if you're dealing with soup. So it's a little bit of that sort of gray area. So if you look at that specific clause that's actually from 62304, and it's got this similar pattern across the whole 62304 document, where it mentions a clause like manufacturer shall include or reference in the software development plan a plan to conduct the activities and tasks of the software risk management process, including the management of risks related to soup. So that whole including of soup is really a common theme across the whole document, where it doesn't specifically state any specifics to what you have to do extra if faced with soup in your design. So the potential issues with that, so of course you may fail certification, or you may have major software issues as a result of soup, which results in a product recall. So what it comes down to is that if you're going to use soup, there's additional risks and someone has to accept the responsibility of those risks.
Yep. George, is it basically, given that some people do it, use these soup-driven interfaces, is it a case that you need to have deep pockets, and that if you're a small startup or a small medium enterprise, that it's just cheaper and easier? I don't quite get what you mean by not easily. I'm assuming, like if you don't want to have to reboot your Windows system in the middle of an operation, obviously, and the hazards analysis, obviously, if there's something like that did happen in the middle of an operation, be catastrophic, then you just have to rule it out. But there's going to be lots of circumstances where it's okay to use one of these interfaces because it's not very time sensitive. It might be, something you do after the operation, where you're just managing your data, and it's okay if it goes down because you can just reboot it and redo it again. So, so what's the bottom line here? When should people rule it in, and when should they rule it out?
Well, there are a few points there. So when I say not easily, that's because an operating system, there's a lot of software behind an operating system, and the fact that you have to validate and verify verifying it is virtually impossible. Validating it may be a little bit more achievable on the basis that you can do some additional risk management and hazard analysis and see that the end result does meet the user needs. But so what it comes down to is, yes, if you have a system where the display of using a smartphone or using an embedded OS display is really a secondary source of information, or it's a secondary action that is not really subject to some kind of critical thing, a critical hazard occurring. So if I've got a device that is being run in the theater, and then everything that's being run on that device does not include any soup or any use of these higher level displays. But then I decide after the surgery, I want to plug my device into another device that then gives me visual feedback of some additional information that I might want to know that is otherwise stored on the device anyway, for example. Well, that's actually okay. And that sort of aspect of that design can then be, the specific aspect of using that LCD display can be moved to a Class A, but the actual firmware running on the device can be deemed Class B. So you can separate out the critical and non-critical parts. Now, the question about, do you have to have deep pockets? It's not about having really deep pockets, but it's about to verify and validate it. But it's about the fact that there is an extra level of responsibility there and someone has to take that responsibility. Now, without just digging your head in the sand and saying, oh yeah, I think it'll be all right, the risk is quite low. So that's what it really comes down to. And it's not an easy one to say when someone can or can't use it. It's just a matter of understanding that there is additional risks that you have to consider. Now, what does that really mean? I mean, well, in Genesis's case, we strive to avoid using where we can in the critical aspects of the design, avoid using some of these higher end soup-based displays. So, you can get LCD screens and touchscreen LCD screens that are completely controlled by a microcontroller. And if that is the only source of information on that medical device and the only way of showing that critical information that would otherwise cause a hazard or a risk of harm to a patient, then we strive to use those displays that are completely controlled by us, so that we know that we don't have to even worry about these additional things that the soup raises.
And can you just, while we're on this screen, clarify the different classes A, B, and C, and how does that relate to the class of the medical device, which is usually thought of in terms of class 1, 2A, 2B, and class 3 devices?
So I'll go back to, so class A, B, and C is specifically referring to the software. So class 1, class 2, and class 3 device being referred to the actual device, the whole device itself, the medical device. And class A, B, and C is referring to the software running on that device. So this is basically what it comes down to. Class A is software that can't contribute to hazards. So if you've got a medical device that can't in any way cause some kind of harm to a patient, and the software running on that can't contribute to that, then you can be deemed a class A. But really, at any point in time, if there's any risk of, even if it's a risk of non-serious injury, so for example, if something happens in the surgery and the patient is not going to die, it's not necessarily going to die from that thing occurring, but it may mean that you have to keep the person under for a little bit longer, and it may mean that it could have other side effects because of the extra anesthetic being used, or something along the lines of that. All those things contribute to additional risk, and that's what sort of drives it towards that class B.
So there is a question here from Matt Davis, which I think you've clarified, and the answer is yes. I think does class A require that the device itself cause the harm, or would a device that gave information leading to a misdiagnosis also be a class A device?
Yeah, so the chance of a misdiagnosis still falls in the same category of class B. It's not just if the device itself is going to cause harm. If you have a device, for example, that is doing some kind of cancer detection or something along the lines of that, if you misdiagnose that person because of some misuse or some issue that appears in the device, then that's considered a potential risk to the patient. So it still falls in the class B. It's not just direct hazards that happen on site at the time.
Okay, I've got 2 people with their hands raised, and look, apologies, people, we're going way over time, but as soon as I saw James's slide, I knew he would. So we've still got 30 people hanging in, so that's great. We've got Pierre Longchamp and then Jeff Sizer. So I'll just go Pierre first, and then Jeff. So Pierre, you've got the mic.
Oh, sorry, I was not intending to necessarily grab the mic. I didn't notice I raised my hand, but I had a question anyway regarding the usability studies that was discussed more in the first half. Wanting to know to what extent you need or can engage patient with remuneration, or if the subject needs to be volunteers, and whether you can engage external organization to handle that for you.
Question
James,
for
answer
James.
that?
We're doing human studies at the moment, which involve a mix of all of that. when we set up a project, we always ask if there's a suitable cohort of people that can be used throughout the course of the project so that we've got access to them. We very much like the idea of volunteers because they'll give you unfiltered feedback. And the important thing is that our design team is actually conducting observational and collaborative research. So what I was talking about earlier about prompting them with questions. If there's a quizzical look, we ask them if there's something that's confusing them, would this make it easier? You can quite often modify and change on the fly to actually start iterating and changing towards that positive outcome. We're doing one at the moment under ethics. That's also another way of doing it, but that tends to be more sophisticated with a smaller group. And again, I think it's an activity that has to be done by the development team, be they software engineers, industrial designers, the people doing the graphic design. You get with the right people in the room, you get a much more nuanced approach to getting the thing right.
Thank you very much.
Okay, thanks a lot. I'll let, if you could just mute yourself, then Pierre and Jeff Sizer, if you obviously had some comments on this.
Yeah, I was just going to make a comment. Can you hear me okay?
Yep.
Yeah, just going to make a comment on the relationship between device class and software class. And it depends very much on what the role of software is in that particular device. So if you have a diagnostic tool or a therapeutic tool where software is at the core and most of the functions of the device are dependent on software, then it's a good rule of thumb is that a class 1 device may have class A software, class 2 device will most probably have class B software, and class 3 device may have class C software as a really rough first pass indicator. But you really do need to look at what the software function is, and you can partition software into different classes for different functions within the device. So for example, if you've got a diagnostic tool, then the software that drives the data gathering and making decisions in relation to diagnosis would clearly be class B. But if you then have software that takes, say, maybe a PDF file printout of those results and conveys that to a PC for storage and printing on a printer, then you can argue that the data communications aspects of that could be class A. So you can partition software in that manner with care, and that gives you some relief from the soup issues in relation to the bits of the software that you are not dependent upon for the formal diagnosis information conveyance. Does get tricky, it needs to be done with care, but you can introduce those sort of levels of subtlety.
Okay, thanks a lot, Jeff. We better finish the presentation, so back to you, George.
Might just go quickly to the end of the slide then. Where are we? Okay. So I think this is actually to you, Tim, because...
Oh, that was the last slide. Yeah. Perfect. Okay, look, don't know if the panelists can see the Q&As. We've got several questions. And we might actually get Luke. See, he's actually a Genesis employee. And he's got 2 questions. And Luke, I might actually get you to, I might unmute you and get you to ask the questions yourself, rather than me read them out, because the first one I don't quite understand and the second one is quite long. So there you go. Luke, if you've got the mic, you unmute yourself.
Hello, can you hear me?
Yes, yes I can.
Hello? Okay.
Yes.
Well, the first one is more of with because since everyone's been using smartphones these days, so that means the user interface is something very familiar to everyone, including probably the users of the medical device. Is there any movement, advantages or disadvantages with using similar user interface in a medical device? So that's the first one. Oh.
Should we answer that, James?
Yeah, sure. I think yes, it's going to probably become more and more. It's going to have more and more resonance with that user group. In what I was saying, it certainly wasn't excluding that there's a divide between consumer user interface and what happens in the medical field. It depends on the user cohort, and it depends on testing. So that's the way I'd answer that, that it's probably going to eventually move more towards people who are more familiar with the things that are in the world at the moment. But it's always got to be tested, and you've got to approach the problem with open eyes.
An interesting one, because, you know, on one hand you got, you know, you, James, saying, you know, yes, we probably are moving towards more smartphone designs. On the other hand, you've got me saying, okay, you can, but be careful, because there are a lot of you know, things that might cause issues for a medical device, that because of that soup, particularly that soup issue. Now, as time progresses, you know, things like iOS, they're starting to become, well, they kind of always have been, and quite reliable, and to some extent you start to build up a trust with them. So the risk that you're taking on for doing, say, an iOS app is starting to reduce to become a lot less risky, because of how thorough their process is. It's particularly Apple in actually allowing apps to actually make it through to deployment. So, you know, times are obviously changing and moving more towards that smartphone design, but it is important to keep in mind that when it's possible to sort of move away from the really critical potential hazardous events occurring, when you can avoid those by having a display that is otherwise not on a smartphone or embedded OS, it's usually favorable to do so, simply for the it makes it a lot easier for getting certification. So TGA certification, you really don't know how the assessor will deem whether or not you've actually done enough to mitigate the use of the risk of soup. Whereas if you have a display that you've completely controlled, everything is under your control, you have complete evidence of your verification and your 6304 process.
Yep.
That's actually quite nicely to the second question. If I may, feel free, Tim, to cut me off. In terms of, so because we were talking about smartphone user interface soup and deep pockets, can you give some situations where it makes sense to use the smartphone user interface or soup, given that this soup or the tools that smartphone developers tend to use allow for faster and arguably really cheaper way to make more screens compared to designing user interface from scratch. And particularly, these tools are tools used by developers that produces products that are used by billions of people, because again, they're using frameworks that are used in your everyday smartphone, while you compare that to a UI from scratch, which will be used by a very few people, in essence tested by a lot less people.
On regards to sort of the cost side of things, I mean, with medical devices, the sort of the truth and reality of the situation is that medical devices are in essence expensive and can cost a lot of money to make. And a part of that, really, that high level of expense is in the software aspect of trying to get everything verified and compliant and certified by the certifier. So the act of using soup in your design, although it may increase the speed of your development, it may actually end up causing further delays in trying to actually prove that the soup you're using does not actually have any additional risks that may occur. You know, using a smartphone, I mean, a crude example is that, you know, you might have some specific issue occur on your screen based on some other auxiliary operating system things that happen, and then suddenly you lose access to that app during something really critical. Now, of course, that can happen on any device, but the fact that you have you don't have these auxiliary operating system processes happening in the background that are out of your control means you have that sort of more control over that verification and validation of the software that you have running on your device. So in terms of an example of who can use it, I would sort of at this point still stick to the concept that if you have something that is, you know, a display that is being used in a critical format, so not just secondary information that is later on used, like Jeff was mentioning, like a web page for a PDF display, but more something that's a lot more critical, that if the display does not display what it needs to correctly, it can lead to some real serious harm to the patient. Maybe that might actually be a sort of the example that James made with that particular patient that got overdosed. I'm not sure if that specific situation was the user interface was specific to the display. That's an example of where, if that display is not showing what it needs to show because of that additional risk, or that hazard that may have occurred, that additional risk that may have occurred by using soup, then that really can be a problematic situation. So,
okay. Thanks, George. We'd better wrap up there. If that's all right.
Yep.
The last question, D. Hood asked, what are the strategies to remove the GUI from critical safety of the device, given the assumed 100% failure of software? So it's a bit of a question out this 100. You know, if you're going to assume all of your software could fail, then what are you going to do about that?
So this is actually one that our Genesis CEO Jeff Sizer is quite passionate about. So if you don't mind, Jeff, do you mind answering that particular one? Just because the aspect of the 100% failure is one that me and you have discussed in the past. I know you've got your very strong opinion about that one.
The 100% failure thing comes out in a technical report on the application of ISO 14971 to software, and prima facie, it's absolutely ridiculous. That means you turn your PC on and it does its first instruction cycle and that fails. So why are we talking to each other now if software always fails 100% of the time? And as I like to say, bugs that occur 100% of the time, I like those because they're easy to find and fix. A rational common sense approach is that 100% failure consideration only makes sense in the context of assessing the device class. So if any software failure can cause a dangerous situation to occur, you use that 100% probability of failure to determine which class the software is. And put things in perspective, I say class A is why bother. Class B is sensible and aligns with good engineering software design practice, as Deanna will well know. If you look at Class C, curiously, the imposition on Class C over and above Class B is not that significant, and also aligns with good engineering practice. So it pays not to get too hung up on the class, and really only fall back to the Class A consideration if you can possibly put your soup into the Class A component. Class A does not require you to stress about soup. So that's really the barrier. But realistically, for any sensible device that's doing a reasonably function critical process, you're going to be dealing with Class B. So to further on the 100% failure thing, I said it is a nonsense. You have to interpret that within the context that makes sense only when assessing the device class, and when you apply 6304 disciplines, of course, that is aimed at reducing the probability of failure of software. So a rational response, since that software doesn't fail all the time.
Okay, look,